What's up guys, it's Simon Fiaz. Today's video is on 2018 AS level question paper 2018 paper 1. State two differences between plum-pudding model and the model of atomic structure used today. So the idea that central nucleus contains protons and neutrons. Electrons are now arranged in energy levels. That's really it. Central nucleus contains protons and neutrons. Electrons are now arranged in energy levels. Deduce the full electron configuration of atom of element R. Well, I know element R has 7 electrons, so it's just going to be 1s2, 2s2, 2p6, right? No, it's going to be 2p5. No, it's not. It's got 7 electrons, so 2p3 then. 1s2, 2s2, 2p3. 2 plus 2 is 4, 4 plus 3 is 7. What is R? Well, I go to the periodic table, 7 electrons, nitrogen, boom, nitrogen. Then it says, introduce the formula compound when R reacts with a group 2 metal in the same period as R. I look at R, nitrogen, same period, group 2 metal. Let's go to group 2, same period, so it's got to be beryllium, right? It's got to be beryllium. When that reacts with beryllium, Be. Well, I know nitrogen, so it's going to be nitrogen and beryllium. Well, beryllium is, nitrogen is going to be charge of a nitrogen ion. Charge of nitrogen. So N3 minus, right? And beryllium, so it's going to be Be3N2. And then you swap the charges. So Be3N2. As formula. Question 2 is question about sodium fluoride. Some toothpaste contains sodium fluoride. Concentration of sodium fluoride can be expressed in parts per million, ppm. 1 ppm represents the concentration of 1 milligram in every 1 kilogram of toothpaste. A 1 gram sample of toothpaste was found to contain this much moles of sodium fluoride. Calculate concentration of sodium fluoride. So what I would do first is, what is the MR of sodium fluoride? 42. Therefore, the mass, moles is mass over MR. I wonder if I could have mass. Mass is going to be the moles times by the MR, so it's going to be and that's in a 1 gram sample. But I don't care about that. First thing I need to do now is I need to find that in 1 ppm represents a concentration of 1 milligram in every 1 kilogram of toothpaste, and I need to times by 1000 to go into kilograms, and then that will give me, because that's in 1 kilogram, that will give me my answer I'm looking for, so 1.210. But then I want it in milligrams, so I need to then times by 1000, so that will give me 1210. And then that's it. Because, yeah, that's it. So 1210. So MR of sodium fluoride. Find out the what's it called? Mass of sodium fluoride in 1 gram. then find it in 1 kilogram, and then find it in milligram, then you get that. So find it in 1 gram, then 1 kilogram, then 1 milligram, and then that's your answer in ppm. Then it says sodium fluoride is toxic in high concentrations. Major health problems can occur if concentration of sodium fluoride are greater than this much grams per kilogram of body mass. To reduce the maximum mass of sodium fluoride in milligrams that a 75 kg person could reach without swallowing toxic concentration. So all I have to do here is it's just going to be, because I know this is greater than this, so the maximum mass 3.19 times by 10 to the power minus 2 times by 75, but that's in kilograms, I want it in grams, so times by 75 times by 1000, then that will give me it in grams, but I want it in milligrams, so then times by 1000 again. That's it. So that times by 7, sorry, no, I don't times by 1000 again, because yes, per kilogram of body mass. So I don't need to convert the kilograms to gram. I know that's per kilogram. So 3.19 times by 10 to the power minus 2 times by 75. That will give you in grams, but I want it in milligrams. And remember, grams to milligrams times by 1000, milligrams to gram divided by 1000. So I want it in milligrams, so 2390. Then it says the concentration of sodium fluoride in a prescription toothpaste is that. Use answer to reduce mass of the exact 75 kg person could swallow without reaching the toxic concentration. So I'm going to do a 2390 divided by 2800, because that's the concentration of toothpaste, and then that's the mass of toothpaste needed, 0.854 kilograms. Identify the diagram that shows the correct relative size of the ions of sodium fluoride. Well, I know negative ions have a larger ionic radius than positive ions, so therefore the answer is going to be B. The idea that, okay, so why? Justify answer. So I know sodium, well, firstly, both Na plus and F minus have the same electron arrangement, or I could say isoelectronic, or same electron arrangement. However, sodium has more protons, so stronger attraction for outer electrons, or sodium has more protons, so attracts outer electrons closer. So B, because negative ions have larger ionic radius than positive ions. Both Na plus and F minus have the same electron arrangement. However, sodium has more protons, so stronger attraction for outer electrons. Question 3. Use the data in table 1 to calculate the value for X and the formula of that. So, I know student heated a solid sample of this for 1 minute to remove water and determine a value for X. Figure 3 shows the apparatus used. Table 1 shows the results recorded. And it says mass of empty evaporating basin, mass of evaporating basin and solid before heating, mass of evaporating basin and solid after heating for 1 minute. Okay. Okay. Heat the solid for 1 minute to remove water. So the mass, if I do this, subtract this, I will find the mass of this without water. So let's try it out. 25.47 minus 24.92, that'll give me 0.55. Sorry, I'm asking the mass of water then. Because to remove water, yeah, that will give me the mass of water. So 25.47 minus 24.92 equals 0.55 grams, and that's of H2O, just so I know. Then if I want to find out the mass of Na2CO3, it's just going to be 25.47 minus 24.35. which is going to be 25.47 minus 24.35. No, sorry, it's not going to be that, is it? It's going to be 25.47 it's going to be 24.92 minus 24.35, and that will give me 0.57 grams of Na2CO3. Then what I do is then I work out the moles. So I work out the moles Na2CO3, which is going to be 0.57 over the mR, which is 106, to moles of H2O, 0.55 over 18. Then I've got the moles. Then what I do is I divide by smallest number mole ratio and get 1 to 5.68. That tells me that's 1, therefore I've got to have 5.68, therefore X is 5.68. So I'll say it again. Do 24.92 minus 25.47 minus 24.92 to find a mass of H2O. Then to find out a mass of Na2CO3, 24.92 minus 24.35. Then work out the moles. Divide by smallest number ratio. Divide by smallest number of moles. You get this ratio, and that's your answer to 2 decimal places. The correct value for X is 10. So that's the difference between the experimental value for X and the correct value. Now, I can't say heat loss or anything, because this is the difference between experimental value and correct value. The idea that it's not heated to constant mass suggests how the procedure could be improved using the same apparatus. While I'd said it's not heated to constant mass. That's why the correct value was X was 10 when it's supposed to was 10, even though I calculated 5.68. Yeah, because it's not heated to constant mass. Therefore, just heat to constant mass. Heat to constant mass. And what this does is makes sure more of the water has been driven off. Heat to constant mass. Sure more of the water has been driven off. Question 4.1. Separate unlabeled solid samples of 3 anhydrous sodium compounds are provided for students to identify test tube reactions. So, stage 1, suggested tests. So, add a hydrochloric acid to all 3. Add water or / make it into a solution. Add AgNO3, silver nitrate. Now the observations, your expected observations, I'll just say observations. Well, Na2CO3, sodium carbonate, what will happen with that? Once we add this, well, this will fizz with acid. Will fizz with acid. Sodium fluoride, NaF, shows no visible change. NaCl gives a white precipitate with AgNO3. Then stage 3, what does it want? It wants me to give equations for any reactions that would take place. Well, I've got sodium carbonate and HNO3. So I've got sodium carbonate, Na2CO3, including state symbols. Okay, well, that's nice, isn't it? Na2CO3 plus 2HNO3 to form 2NaNO3 plus CO2 plus H2O. And then the other one, AgNO3, silver nitrate plus NaCl. Well, that you just form silver nitrate NaCl, you form AgCl plus NaNO3. NO2CO3 plus 2HNO3 or 2NaO3, NO3 plus CO2 plus H2O, AgNO3 plus NaCl, arrow AgCl plus NaNO3. Question 5, question about equilibrium, states the time to nearest minute when equilibrium is first established. Well, it's just going to be here. 3 minutes, first established 3 minutes. Reason being, concentrations. Now I need to apply it to the question. I don't want to say concentration of reactants and that is the same. I'll say concentration of O2 and SO3. Concentrations of O2 and SO3 remain constant. I'm not saying they're the same. I'm saying they remain constant. Sketch on the graph how the concentration of sulfur dioxide changes over these 6 minutes at a temperature T1. At T1. So it should look some begin at origin. That's something like that because yeah, over these 6 minutes. Then it says temperature was changed to T2. Mixture left establishing new equilibrium. In the new equilibrium mixture concentration of sulfur trioxide was found to be 0.07. Sulfur trioxide 0.07. Well, here I've got 0.1. This is used which are T1 and T2 is a high temperature. There is 0.07. And that's for what's that called? That's for T2. Well, then that's going to be a which one's the higher temperature? This is very complicated. Like you need to think about this, but this is my thought process. T2, its concentration of sulfur trioxide was 0.07, when in this case it's 0.1 clearly. So 0.1 to 0.07, it's decreased. So if it's decreased, I know the forward reaction is endothermic because delta H is positive. And if it's decreased SO2, so therefore it's got to shift here. Why would it shift in the exothermic direction? Well, because I increase the temperature, therefore shifts in the exothermic direction to oppose increase, therefore decrease temperature. Because if I lower the temperature, then it will shift right side. So T2 is going to be the higher temperature. Reason being, I would say equilibrium has shifted to the right hand side / forward / endothermic direction. Equilibrium as opposed to increase in temperature, hence equilibrium moves to decrease the temperature. Oh, sulfur trioxide. Yeah, sulfur trioxide. Well, originally, sorry, I thought that was sulfur trioxide, that's sulfur dioxide. So originally this 1 to 0.07, and the forward reaction is endothermic, and I've got less of this. So what will happen to the temperature? Well, the temperature increases, then yeah, it's going to shift to the right hand side, not the left hand side. It's going to shift to the right hand side, endothermic direction, opposing increased temperature, and SO3 would decrease. Question 6. Define the term relative molecular mass, aka MR. Average mass of one molecule on a scale when atom of carbon 12 is 12. Average mass of one molecule on a scale when atom of carbon 12 is 12. Determine the relative molecular mass of Y. Well, first thing I'm going to have to do is use this. I'm going to do 10.91 minus 10.70. Find out the mass of this, y, which is giving me 0.21 grams. Now I'm going to have to obviously use PV equals nRT. That's the first step. Then I need to rearrange it to get N, which is PV divided by RT. Then I'm going to substitute my values in, so N is equal to P in pascals, pressure in pascals, 102,000 pascals, times by the volume, obviously meters cubed, divided by R, 8.31, times by temperature in Kelvin, gives me degrees Celsius, 98.1 plus 273. That's how you convert from degrees Celsius to Kelvin. Times by the volume. Well, the volume, this is probably going to be the most trickiest in my opinion to convert. 85 centimeters cubed. So dm cubed, I always remember like the d block is in the middle of the periodic table, so it's in the middle. So dm cubed is in the middle. Now which one's on the left, which one's on the right? Well, meters cubed is on the left hand side, centimeters cubed is on the right hand side, and I want to go from centimeters cubed to meters cubed, so I'm going to divide by 1000, divide by 1000 again. So it's going to be 85 times by 10 to the power minus 6. 85 times by 10 to the power minus 6. That will give me the number of moles. I've got the mass. Moles is mass, so the MR is going to be the mass. 0.21 over the number of moles. So let's see if I'm even right. So 102,000 times by 85 times by 10 to the power minus 6 divided by 8.31 times by 98.1 plus 2 plus 273. You get that, and then you can get the MR 74.7. Yeah. Then it says some of the liquid injected did not evaporate because it dripped into the gas syringe nozzle outside the oven. Explain how this would affect the value of MRY calculated from experimental results. Well, if you think about it, some of the liquid injected did not evaporate because it dripped out. Well, that means lower volume would be recorded. So what happened to the MR? Well, if I got a lower volume recorded, the MR would be greater than the real MR. Lower volume recorded, MR would be greater than real MR. Due to oxidation of chlorine HClO and oxidation of chlorine HCl. In the HClO, oxygen minus 2 plus 1, so it's going to be plus 1. Minus 2 plus 1 minus 1. Yeah, it's going to be plus 1. 2 half equation oxidation in this redox reaction. So I've got Cl2 plus 2H2O. 2HClO plus 2H plus 2B minus the reduction half equation, Cl2 plus 2H plus 2B minus arrow 2HCl. Going to equation for reaction sodium chlorine and sodium hydroxide. Cl2 is 2NaOH arrow NaCl plus NaClO plus H2O. Cl2 plus 2NaOH are NaCl plus NaClO plus H2O. And these two equations, I haven't really seen these, so I'm going to write these down if I carry on. So, oxidation, Cl2 plus 2H2O. Did I say 2H2O? Yeah. 2H2O. I wrote 2HClO plus 2H plus 2 minus. And then the reduction. Question 7. Point 4. Okay, it says concentration of this can be found by this sample of bleach solution found this, which concentration of this potassium iodide is this to this. So I'd find out the moles of ClO minus 0.0109 times by 20 divided by 1000. And then, because I know it's a 1 to 2 mole ratio, potassium iodide, well then, the moles of potassium iodide, Ki equals 0.0109 times by 20 divided by 1000. That just times by 2, because 1 to 2 mole ratio. But I want the mass. Moles is mass over mR. Mass is going to be the moles, this times by the mR potassium iodide. That will give me the mass in grams, but I want it in milligrams. How do I go from grams to milligrams? I want to go from grams to milligrams, that times by 1000, and times my final answer by 1000. That will give me my answer. And so find out the moles. 0.0109 times by 20 divided by 1000. 1, 2, 3, 0.02. Then times by 2. Then find out the mass. And you should then times by 1000. Don't forget to do that part. Grams to milligrams. 72.4 milligrams. State observation. Black solid forms. Black solid. Black solid forms. Or we could say turns brown. Solution in brackets. Question 7.5. Given the equation for decomposition of potassium chlorate. Decomposition. Now, entropy of formation is something like, I'm just giving an example. Let's say I said CO2, entropy of formation of CO2, that's carbon plus O2. Fe2O3, 2Fe plus 3 over 2O2, right? Balance. This is a decomposition of potassium chlorate, and I know potassium chlorate is KClO4. So I'm going to this to KCl plus O2. 2O2 doesn't want state state symbols. It doesn't ask for any, so we don't need to do any. There you go. Then it says calculate enthalpy change for this reaction. Well, I know enthalpy change is enthalpy. Obviously, this is formation data because that little f tells me it's formation data. Formation data. So enthalpy of products minus enthalpy of reactants. So it's going to be enthalpy of products minus 436 minus 434. And you might be wondering, what about the O2? Well, O2 is a single element by itself, so that's going to be 0 anyway. So, and then that becomes plus 2 plus that, so minus 436 plus 424 minus 2. Because just multiply minus 1. Question 8. Sample of bromines analyzed in thermoflight mass spectrometer and found to contain two isotopes, 79Br and 81Br. After electron impact ionization, all the ions were accelerated to the same kinetic energy. 12 if light shoot out that long, calculate mass of one ion of that. So first thing first, mass of 79Br plus ion equals 79 divided by 6.022 times by 10 to the power 23 times by 1000, coming in kilograms, and divided by that. So that should give you 1.31 times by 10 to the power minus 5 kg. I'd calculate the time for this ion to calculate. Well, I'll calculate the mass of this. I'll order to calculate time, but now I can find out the velocity. Actually, not even the velocity. Yeah, I can find the velocity. 0.940 divided by time taken for 79Br plus ion. 6.69 times by 10 to the power minus 4. And now that I've got the velocity, I can find out the distance. Distance is velocity times by time. And I've got the time. What am I doing? Velocity is distance divided by time. Distance is velocity times by time. But then I've got the velocity, then the distance is velocity times by time. And the velocity is that, and the time taken is that. Okay, let's just find out the velocity. And that will give me 142 meters per second divided by -1. Now, instead of doing anything else, I can just work out the kinetic energy. That's what I need to do. Don't to work out the kinetic energy. Then, okay, so then I find out the kinetic energy. So Ke equals the half mass of the 79 plus ion times by velocity squared, which is a start squared. That will give me 1.32 times by 10 to the power minus 19 joules. Let's fill this in. 1.31 10 to the power minus 25 kg. That's the kinetic energy. But I want the velocity. Then velocity is square root of 2 ke divided by m, and then use let me try my way firstly. Yeah, I get the velocity. Velocity distance divided by time distance is my answer. Times by the time. 1.95, and then divide the time for that. So velocity is distance divided by time. Time is the distance divided by velocity. Velocity is square root of 2 ke. So then it'd be 0.95 divided by, well, then I need to do square root of 2 times by ke. Yeah, that's the problem. I don't have ke, so my method wouldn't work anyway. So find out the mass, use velocity, then work out ke, then work out velocity, then work out the time taken. I've already given the distance. That's why I misread. That's why. Yeah. Time taken. Well, then that will give you the answer of 1.40 times by 10 to the power 3. Oh no. That's the velocity. So the answer for second 6.80 times by 10 to the power minus 4 seconds. Explain how ions are detected relative abundance is measured in a thermoflat mass spectrometer. Ions hit the detector / negative plate and gains an electron. Relative abundance is proportional to the size of current. True shape of krypton difluoride molecule KRFF. By looking at the periodic table, KR is in group 0, so it's got attached to 2, so it's going to have 6 lone pairs of electrons. So we're going to have 1, 2, and 2, and another 2 here. It's obviously going to be a linear shape, but the bond angle is also going to be 180 degrees as well. Explain how lone pairs of oxygen atom influence the bond angle of oxygen difluoride. Lone pairs repel more than bonding pairs of electrons. Bond angle will be lower. Oxygen difluoride, yeah, bond angle will be lower in oxygen difluoride. Reduce the type of intermolecular force in SiF4. Van der Waals forces. Explanation: how it arises when another type exists in a sample of SiF4. Uneven distribution of electrons in one molecule induces dipole in neighboring molecule. Symmetrical molecule, hence dipoles cancel. And then there was another previous question, I think it was on the last past paper, maybe the year before that. It was like, explain how permanent dipole forces arise, and the idea that first things first, difference in electronegativity leads to bond polarity. Molecule has an overall permanent dipole, there is an attraction between delta positive on one molecule and delta negative on another molecule. So difference in electronegativity leads to multipolarity. Molecules are over permanent dipole. Attraction between delta positive one molecule and delta negative another molecule. Very similar to this, like a 3 marker. How van der Waals forces arise, permanent dipole forces. So van der Waals forces, uneven distribution of electrons one molecule induces dipole in neighboring molecule, symmetrical molecules, hence dipoles cancel out. And then that is it for section B, the past paper questions.